is Antonio Fortunato, and I am Deputy Head of Crew Operations for the European Astronaut Center in Cologne. The topic of this lesson is the International Space Station. As a vehicle, we will discuss its modules, its main capabilities, and to a lesser extent, its operations. So, let's talk about the unpressurized elements. And here, really, we want to discuss just the major highlights. This is true both for the outside and for the inside of the station. The space station is a very large vehicle, has been in space for a very long time, and it is really not possible to get into all the details about how it works and the components it is made of. So I will really just be picking up highlights and discussing them. Well, when we look at the ISS from the outside, probably the most distinctive feature are the solar panels. The station is equipped with 8 solar array wings. Each wing is 34 meters in length by 12 meters in width, and it can generate up to 34 kilowatts of electrical power. The solar panels, just for clarity, are those here encircled in red. Now, as you can imagine, a panel that is about 30 meters in length cannot be possibly launched to space in one go. There is no launch vehicle, there has never been any launch vehicle with that kind of volume capacity. So the solar panels of the ISS, the solar array wings, were flown in the cargo bay of the space shuttle in a folded configuration. And here you see a picture of one of the solar panels immediately after being installed on the ISS. And it is interesting to see the proportion between the size of the solar array wing, even just in a fully folded configuration, and the astronaut in EVA. So the panels were taken out of the cargo bay of the space shuttle, they were installed on the outside of the space station, and then very careful, very slow unfolding operation started to take them to their full extension. When fully extended, this is what the solar panels look like. Here you have really 2 solar array wings just basically superimposed in perspective. As you can imagine, unfolding such a big solar array wing is a very delicate operation. Things can go wrong, and historically things did go wrong. Specifically in 2007, one of the solar array wings was installed and unfolded. At about 80% deployment, one of the guiding wires snapped and it damaged the solar array wing. This was a very undesirable situation for a number of reasons. First of all, it is not possible to leave such a large structure not fully deployed and with such a large tier. It either needs to be jettisoned or it needs to be repaired. And jettisoning a solar array wing wasn't really an option at that point. The power that solar array wing had to generate was badly needed to install the modules of the smaller international partners, so the Columbus module for ESA and the Japanese experiment module for Japan. So in the end, it was decided to go ahead with the repair, but it wasn't a very easy repair. And this is because, first of all, the area where the damage occurred is not readily accessible to astronauts in EVA. It is simply not possible for an astronaut to climb the structures and reach that place and implement the repair. One alternative, of course, to direct access is to use the station robotic arm, but the station robotic arm isn't nearly long enough for an astronaut to reach the damaged area, not in its normal configuration. In fact, the extension boom of the shuttle robotic arm had to be installed on top of the station robotic arm just to make it long enough for Scott Parazinski, the astronaut you see in the picture in EVA, to reach the damaged area. Another problem was the fact that this was the repair of a solar array, and a solar array is something that generates electrical power as long as there is radiation from the sun hitting its cells. It cannot be switched off, which means that there was a very real issue with electrocuting hazards, with electrical arcing, which meant that all the tools that Scott Parazinski used during the repair had to be electrically insulated, and also the metallic parts of the spacesuit had to be electrically insulated. Also, it took 45 minutes to maneuver the astronaut from the main body of the space station to the solar array. And this was a problem because normally, according to ISS rule, an astronaut cannot be further away than 30 minutes from the airlock. And that's because if there is a problem with the spacesuit, the secondary oxygen system only lasts for about 30 minutes. In any case, it was a very complex repair, but it was also a very successful repair. Scott Parazinski managed to install 5 cuffs that basically stitched together the 2 parts of the tier. And the solar array wings is still there, it's still working very well and providing power to the ISS. One thing that is also interesting about that specific mission is the fact that it marked the first time a space shuttle was docked to the ISS, and both the space shuttle commander and the station commander were women. Pat Melroy was the shuttle commander and Peggy Whitson the ISS commander. Now, solar cells, solar arrays, solar panels only generate optimal power if they're pointing directly to the sun. The ISS as such flies normally in an attitude ensuring that one side of the station is always point in the direction of the surface, which means that if we kept the solar panels rigid with the rest of the ISS structure, the panels would never be generating optimal power. So we need joints to ensure that the panels can track the position of the sun in the sky as the station flies around the planet. There are 2 types of joints available. One type is the beta gimbal assembly. Each solar array wing has a beta gimbal assembly. This beta gimbal assembly allows the solar panel to rotate around its longitudinal axis, and this isn't really a continuous 360 degree per orbit rotation. The BGAs are only used to basically perform fine adjustment in the direction of the solar panels. What really does most of the job is the solar alpha rotary joint, and there are 2 surges, one on the port side, one on the starboard side, and what the surges do is really to rotate an entire piece of truss supporting 4 solar array wings around the longitudinal axis of the ISS truss. It is a 360 degree rotation per orbit, and the surge actually does not need to be reeled back. The rotation can be continuous, and it is still possible to transfer power from the solar arrays, and by the way, the batteries that are in the same section of the truss, to the rest of the space station. One important point to make here is that the solar panels are the one and only power source for the ISS. The ISS has nothing else to generate power. There are no diesel generators, there are no nuclear reactors, there are no radioelectric thermal generators. The ISS from that point of view can be really considered as a green vehicle. Just to give a sense of perspective of how big those joints are, you see here in the picture two astronauts in spacewalk, and they are working exactly in proximity of the solar alpha rotary joint. In the background on the top left you see one of the beta gimbal assemblies. If the solar panels are the most visible feature of the ISS, the thermal radiators are probably second most visible. The problem of heat dissipation in space is a very complex one. Any piece of equipment that uses electricity will generate a certain amount of heat, and this heat must be dissipated in some way to avoid damage to this piece of equipment. Now, on Earth, heat dissipation is helped by natural convection. Natural convection simply means that if I have something that is generating heat, the air around this piece of equipment will become hot, and because it becomes hot, it will become lighter than the surrounding air, and it will tend to move up and be replaced by cold air that in turn will be heated up and again move up. Now, this mechanism does not work in microgravity. There is not light and heavy, so special care and special attention must be taken to dissipate the heat that is generated all over the station. The station is equipped with a very complex thermal control system. The thermal control system is divided really in two parts. There is an internal thermal control system and there is an external thermal control system. The internal thermal control system, as the name suggests, takes care of removing heat from the equipment that is inside the station and take it to some interface heat exchangers. At the interface heat exchangers, the heat is taken by the external thermal control system and is carried from the point where it is collected to the thermal radiators. And the thermal radiators take care of dissipating, radiating as much of this thermal load as possible to outer space. In a way, the thermal radiators work in an opposite way to the solar panels. While we want the solar panels to always be pointing in the direction of the sun, we want the thermal radiators to always be pointing in the direction of deep space. And that is why also the thermal radiators have a rotary joint. This is called targe, and this rotary joint allows the thermal radiator to rotate around its longitudinal axis. There are a couple of interesting points that could be made about the thermal control system of the ISS. First and foremost, I mentioned that there are two thermal control systems, an internal one and an external one. Well, why is it so? Well, there are different issues, and the first and most important one is safety. To take heat from the place where it is generated to the place where it is dissipated, obviously you need a medium, and usually you need a fluid that is circulated in a loop. And the problem is that the fluids that are most efficient in carrying this heat are usually not really friendly when it comes to human life. So, for instance, one very good fluid that could be used to move heat from one point to another is pure ammonia. But as you know, pure ammonia is extremely toxic, so it is not safe to use it, for instance, on the inside of the station. That is why we have two separate thermal control loops, and inside the station water is used as a transfer medium, while outside of the station the pure ammonia is circulated to take the heat from the interface heat exchangers all the way to the radiators. This is one important point. The other important point, if you look at the picture of the ISS, you will notice that there are really two different sets of radiators. You have the big radiators, those are the ones closer to the stack, closer to the pressurized part of the ISS. And then you have smaller radiators closer to the solar array wings. Now, why aren't we using the same radiators to dissipate the heat that is generated inside the station and to dissipate the heat that is generated in the section where all the power generating equipment is located? Well, you remember I mentioned before that the solar alpha rotary joint is such that it rotates 360 degrees per orbit and it doesn't need to be reeled back, which means that it would be extremely difficult, if not impossible, to have fluids, ammonia in this case, moving from the external part of the truss to the internal part of the truss. That is why those external sections have radiators of their own.